Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good morning. It's my very great pleasure to introduce Renee Mueller today. He's a PhD candidate in ETH Zurich in the systems group. His advisor is Gustavo Alonso, and his work tries to accelerate database operations using FPGAs. That's the topic of his presentation today, stream processing on bare metal. So please welcome Renee Mueller.
Thanks, Ken. Thank you for the introduction. So what we're going to talk about today is stream processing, as the title says, on bare metal. So what does it mean? What I'm going to show you is how we translate execution plans, traditional execution plans you find in data processing applications, and cast those plans into digital hardware circuits. Of course, I have to tell you why this makes sense in the end. And why it's worthwhile to go all the way down to the hardware level. So let me just start with the motivation, and the use case that was brought to us comes from the finance industry. In particular, a large Swiss bank approached us and said, well, we're doing this automated financial trading, so option trading done by machines. And we're facing the problem that, first of all, we need to operate on large data volumes at a very low with very low latency constraints. So here's basically the sort of outline why this might become a problem. So these companies, they get their data stream from exchanges, New York Stock Exchange, the Swiss Stock Exchange, for example. And what they're getting is essentially aggregated market data, bits data, sell data from the order book. And it's a massive amount of data. Here I sketched the amount of messages per second over the past few years and the projection outward for the coming years. And clearly, as everybody can see here, the data volume is going to increase. At the same time, latency is crucial. So this guy tells us, well, for every microsecond you can reduce the processing latency. That gives us such and such millions of profit.
That gets to be $1 trillion per second, which even with a crazy financial market looks high to me.
These are essentially this is million messages per second. So
messages, I believe. Your messages or dollars? You said dollars, sir.
This is dollars.
$1 trillion per second business?
It's in the end of the month. Apparently, that's what these are the numbers. These are the numbers that were brought up to us. In particular, it seems to be that they put their data center really next to the stock exchange to reduce latency, and that, of course, costs money. And they wouldn't do that if it would be pointless. Yep. So it's a high data volume, and what they have to do is they have to deal with this data volume that is sent over really small UDP packets. And they're facing the problem really, how do we handle this load in a reasonable manner? So the good thing here is that life is not as bad as automatic trading systems only work on a subset. For example, you only want to trade, today you only trade Microsoft stock or Google stock. So you can do filtering on those market stream items. And for the high-level algorithms, they also are interested in aggregate statistics on that stream. So you have now 2 points here, which is selection of data items, and the second one is aggregation, computing essentially averages over time. And this both translates into data reduction. And so the idea is, well, what happens if you can sort of offload this aggregation processing somewhere else and leave the CPU to do the really useful work on on the actual trading algorithms and the decision algorithms. So that's where it started, and the idea was, well, just pick an idea, just pick FPGAs, maybe they can help here. And I'm not sure, apparently many of you are familiar with FPGAs, so I might go quickly over that, but give here a quick introduction so that everybody is sort of on the same page. FPGAs are silicon chips that provide you a large number of logic gates. You can then configure, you can determine what functionality they implement and how you wire them up. So you have this logic layer and there's a configuration layer underneath that will tell how you wire up the logic gates and what functionality they implement. So if you just, it's the last FPGA slide here, if you just zoom in on one of these FPGA chips, we essentially have a number of configurable logic blocks that contains flip-flops and combinatorial logic circuits, as well as an interconnect, and there's some blocks that make sure that you can feed data in and out of the chip. So the question is still there, why FPGAs? Now the reason why FPGAs are interesting in this use case is that you can put them in a particular system configuration. And here are the two system configurations we're looking at. So one configuration, the configuration A here on top, is where we put the FPGA in the data path. So this assumption is we're trying to offload as much processing of the traditional CPU-based system. So we plug it between the network and the host system, and we're trying to offload as much data and do some pre-processing here. I sketched that by this query plan, which we do in hardware here. We might also need to do here a simple network protocol handling. So in the system I built contains a simple UDP IP engine implemented on the FPGA fabric that is able to receive those UDP packets, extract the payload in there, and then feed it through this query plan. I'm going to show you in the remainder of the talk how such query circuits then in the end look like. A second approach to this is if you use the FPGA as sort of a coprocessor. It's similar to the way how you use GPUs. You continue processing in traditional software stack. At some point, you copy the data over to the FPGA or the external memory connected to the FPGA. You continue execution on the FPGA. At some point, when the computation is complete, you copy the result back and resume execution on the CPU. So that's the CPU circuit, CPU path. For the stock exchange example, what really makes a difference is this configuration up here. That's what I'm going to focus next. Yes?
So the reason that you're moving computation to the FPGA is to offload CPU computations, or is there any other reason? So is that the main reason?
Yes. So there are two reasons. First of all, you're right. You can offload work, which is not a bad thing anyway. And the second thing is, which I'm going to show you next, is that you can actually do things on the FPGA you have difficulties on a traditional CPU.
So coming back to the first reason, is it true that most of these automated stock trading streaming queries are CPU bound, or are they typically memory bound?
It depends. So if you're looking higher up in the decision, where the decision functionality is, there are CPU bound algorithms as what we know. If it comes to the data extraction and pre-processing, there's clearly I/O bound. And we're looking at this I/O bound part at the moment. So here's a simple example, because we couldn't really believe what's happening. So we just said, all right, let's simulate this. We come up with a simple artificial data stream. So we made the problem artificially bad, as you can possibly get. simple, really short tuples and only one tuple per packet, resulting in a minimum Ethernet size, frame size of 64 bytes. And we just try to see how much we can actually pump out of a system. So, for example, if you have 1 million frames per second, this then only saturates half of your gigabit Ethernet link. Next, we just see how much data makes it up, reaches the application stack on a traditional PC or desk server system. So here we saw the type of query implemented. This is a stream SQL query that just does the following. It will create a time-based window over 1 second that is then tumbling. So it will produce a result every second over all tuples that have been received over the last second, and we'll just count the number of tuples we receive. And we just implement that, no fancy interrupt collision, no polling mode, just simple C library and UDP sockets. And this is what ends up at the receiver. So if you're pumping in data at the rate of 300,000 packets a second, we're losing about 40%. And if you're increasing that number to 1 million, we're dropping 2/3. Of course, you may use interrupt collision. What actually happens here is that the receiver is not fast enough emptying the message queues, so the message queues will overflow as the interrupt rate is too high. So what you could do here in order to increase these numbers is, of course, you can switch one core to do polling mode, or you can do interrupt collision, which introduces latency, but definitely reduces the interrupt service rate, because the overall data rate in the end is not that high. So, but this is just to show that there might be a problem out there if one is not really careful. And now the FPGA solution, the data just comes in on the wire. We have the data on the wire directly from the network controller. And what we can do here, we can process the data at wire speed. We can at least receive the data at wire speed. What we now need to show is that we can process these data through our query plan also at the same speed. So we're definitely not input bound. The question is whether we are good enough in our circuits to do this type of processing, so that we are not pushing back or holding back the data through our query circuits. So in the remainder of the talk, I'm going to focus on 2 simple queries, on a simplified view of this stock exchange problem. So we're looking at a simple stream. This is a ticker stream. And 2 streaming queries that operate on that ticker stream. For example, that ticker stream has a sequence number. It has a symbol UBS, Novartis, ABB, companies that are traded in the Swiss stock exchange, the price of a share and the volume. And then you have 2 queries, 2 separate queries here, which we're going to look at. One is a simple selective query, this Q1, that will just return all large UBS trades, so trades where the symbol is UBS and a volume like greater than 100,000 shares. The result of that query, of course, is another stream. That's why we have this stream processing. So a stream comes in, the continuous query sits on the chip and produces an output stream. The second query is more complicated. It contains averages. So it's the second use case where we do stream statistics. And the goal here is to find out the average price of each of these symbols over the last 10 minutes, and we want the result every minute. And that's in sort of awkward fashion how you express this in stream SQL. You partition the stream by the symbol. You have this average, aggregate, and here's this window definition. So it's a time-based window that contains 600 seconds, so 10 minutes, and you slide that window every minute, so every 60 seconds. These are these 2 types of query we're going to look at. So now since I've motivated all of that, so what I'm going to show now? I'm going to show first how such query circuits look like and how you translate out queries. And then I want to spend some more time on how you would implement stream-based window joins. Database peoples are all after joins, and here's a nice idea that makes use of FPGA logic and the parallelism the FPGA provides, and that perfectly scales within a chip and across multiple chips. So that's where I will spend the most of the time for this talk. So how do we get from a query to a hardware circuit? In general, how the design workflow for FPGAs is, you start with your digital circuit, you express it in some form of definition, hardware specification language. So, for example, VHDL. You run it through a magic box of tools that will compile that code and place and route the components on the chip. And what you're getting then is a binary blob that you download on the FPGA that will then configure what functionality these gates implement. This is the traditional FPGA workflow. So what we're now doing is basically a compiler that sits on top and accepts these algebraic query execution plans. In this talk, I won't use the plan notation. I will use just simple SQL queries. But you may think of that SQL queries, you're actually having execution plans containing these stream operators that are well studied in literature. And so here, the compiler will take those execution plans and decide, well, how do I cast this into logic circuits, and then compile and then produce VHDL code we then feed into the traditional FPGA design flow. So the idea is, ideally, you wouldn't have to worry about, as a database person, you don't have to worry about this part here. That's taken care of by the compiler. Yes?
So are there limitations on how often you can reprogram these FPGAs?
This configuration layer is, on most FPGAs, is implemented as BRAM. So as SRAM cells. So when you power up the FPGA, you have to program it. So the program is volatile on the chip. So you can even reprogram the chip at runtime if you want to. So there's no limitation essentially of how many times you can program that chip. What might be of concern is how long this process takes. So we worked on a paper where this process here took 11 days.
How much?
11 days. And but we were pushing the circuit a bit to the limit. But we came up with a successful place and routing in the end. So here's the one and only slide that basically tells you essentially all the magic. So here's the example for that selective query where we want to figure out all large volume UBS trades. And the approach here is essentially extremely simple. We just go parallel. So if you have an n-bit tuple, we just use n parallel wires. So this works here, at least conceptually. And then we have additional wire that tells us whether there's valid data on the other wires. So here's the circuit that sort of reflects how it's mapped on the chip. So data comes in at the bottom and then flows upwards and exits the query circuit on the top. The compiler then, these black bars here represent register stages. So you can think of this as a pipeline. And the compiler now, what they show here is the purely mechanical translation of the circuit without any additional knowledge. Yes?
That's an and. Could you have done an or?
Here? Yes, sure. Here, yes, sure.
You could.
Yeah.
Because in an and, things fall by the wayside and never come back. In an or, they may have to.
No, you can.
Take each other.
But the way this works here is that we make, first of all these predicates and the expressions explicit, which means that the result of these predicates will create additional values in the output schema. So we have here an output schema for A for that expression, there's an output schema B for, well, the other way around, for this one. And this AND then corresponds to this unit here. So we have these arithmetic and Boolean operations up here in the circles. And the selection in the end is essentially only a simple AND gate that will tell us, well, is the predicate matched here, matched with the previous data valid signal that will then drive the data valid signal on the next stage.
Do you actually split the symbol and the volume check into separate pipeline stages?
You split the symbol.
You're checking the symbol in one pipeline.
I'll come. This is just a mechanical translation of what you might do. So you might rearrange. You do definitely rearrange the operations. I will talk about spend a few words on that later on. So the data moves along this pipeline. Oh, the last step I forgot to mention this one. So this is selection, and the last step is projection. So we're projecting. We're only interested in price and volume. So we're projecting away all other attributes we don't need. And projection is simple, we just don't connect those wires. And what will happen is that the tool is smart enough to detect, well, these are dangling wires, so it can prune back the circuit all the way back to here and all the way back to here. And this essentially gives us projection pushdown, what database people call projection pushdown. And that's taken care of by the FPGA design tools. So the data here clearly moves in this pipeline, and if these are registers, we have 1, 2, 3, 4, 5 stages. So we have 5 cycle latency through this pipeline. Since this is fully pipelined, I can add a new tuple every clock tick because it flows through this pipeline. And if I plug this to my gigabit Ethernet core, which clocks at 125 megahertz. That's the typical setting here I'm using to make life matters simple. Here's the throughput I'm getting. I'm getting 125 million tuples through this simple pipeline. At the latency here of 40 nanoseconds, so this corresponds to these 5 cycles here. The optimization question, and I think that's where your question was hinting at. Of course, I can now play a couple of tricks. Maybe this mechanical translation is not the best way to do. On the other hand, one has to be careful not to interfere with the FPGA tools so much because there's a lot of knowledge also in those tools. For example, what I can clearly do here, I can move this operation down here and I can remove one stage. What I could also do is I can just remove one register state completely. So basically then collapsing these 3 stages in one stage, what will happen then is the longest signal path will be, well, across here through this additional gate. Will increase the signal latency, which you then make me use a lower clock frequency, as the longest signal path determines the maximum clock frequency. But here I can have sort of a possibility to trade in latency versus throughput. I might go and say, well, for this very simple circuit, I might decide, well, I just remove all of these stages and I can do this in one cycle. If the latencies I get through this gate is not preventing me from ending up with a throughput that is too low for my requirements. So that's what I'm going to show next here is that's the simple, essentially it's a data flow graph if you think of it. What I'm going to show you next is how we do stream joins. And it turns out that stream joins are extremely important for database people. So when we first published it without stream joins, we got the review, what about joins? It has to do joins. So we spent some time thinking about this, and I think we came up with a kind of interesting idea. So what are window-based stream joins? So the setup is maybe from RFID data, where we have RFID readers on 2 shelves, and then we want to figure out when one event happens, within X minutes, the other event needs to happen. So you need to join those 2 streams within time windows. So stream join essentially is, if the streams are infinite, you have the traditional join operator you have in relational database is a blocking operator, right? So you can't produce any tuples until you have seen the end of it. So the way around this in streaming application is you just provide a finite horizon, which is done here through this window. This window may be tuples, tuple-based. For example, it may include the last 50 tuples, 1,000 tuples, or it may be time-based. Say it may include all tuples from the last 15 minutes. So then what you're ending up here is essentially 2 relations, and the join becomes sort of relational, a join you can do here. So why is this difficult, and how does this join work? What you essentially have to do is you have to do this n-squared matching. There's a way around this. You can do hashing, but you need to sort of pair up these elements, which, depending how you put it, in the end results to sort of central coordination. And for the FPGA, we really don't want to have this centralized organization, because that would basically limit the scalability, and we're not making use of the amount of parallel gates we have. So here's an idea, and we came across this idea when we looked at sports. Maybe you know from football, soccer, ice hockey, they have this, at the end of the game, they have this shake of hands. So the problem there is you want to match every player of Team A with every player of Team B. And if you look at how they do this, they let the players line up and walk by each other in opposite directions. So here's I like hockey, so that's why I picked the hockey players. I did the slides before the American team kicked out the Swiss team of the Olympics, but I think I can still use the slides. So here's what happens. The player in blue walk in this direction, the players in yellow in the other direction. You can see there are many parallel handshakes going on at the same time. That's one thing. So we can declare, well, that's obviously a parallel solution. This picture has more insight, basically, because you can see here that all this interaction is local. There's no central coordination because, well, the players have limited reach in their arms. This seems to be a nice approach for scalability that might just as well also work for FPGAs. And we can really take this picture and directly translate that onto the chip. So here's what we do. We have the players here from stream R and the players from stream S crossing each other in opposite directions, and the window is basically what limits the segment where the interaction happens. These windows may have different sizes here, so 4 compared to what's that, 7, and we do the matching in between. Somehow, I will talk about more how we do this. So, as the data moves through this window, it will eventually encounter any tuple that sits in that window as it moves through. So we're not changing any semantics we're not missing any joins we would have in the other traditional nested loop join or relational join. So I have to explain you how we do these comparisons and how we make this thing parallel. So how do we make this thing parallel? So the idea is quite simple. Well, we just partition the window across multiple cores. Cores may here refer to cores that are units within an FPGA. These may refer to a core like SPEs you have on the cell, or this may even refer to cores you have in a traditional multi-core. So you partition the window, and you do this join in between, the only thing you need to care, you watch out for, is what happens in this intersection here. So in the interest of time, I only tell you how we do this on the FPGA. If you want to know more about that, I can tell you how this directly maps to multi-core CPUs. You can just do the same trick. So what we now need to do is, for each core, is we need to figure out a scheme, what happens when a new tuple arrives. And then we can also play out this parallelism. Essentially, what matters is that you only maintain the semantics at the edge of the core. You can implement the join within a core in any sort you want. You could do hash join, you could do merge join, you could do this with loop join, or you could do parallel join. Was there a question?
So I have a kind of more basic question. How do you even set up the windows? So I can understand if your query is give me the last 100 occurrences or something, right? Because every time you get one in, you push one out. But what happens when it's time-based, right? You may have to evacuate you may have to toss a lot of things out
Yes.
at once. Or you may have to receive a lot of input all at once. So how
that's indeed the case. We are not doing time-based windows on the FPGA because you may run into the problem that within a window you have potentially unbounded amount of storage you need. It turns out for CPU-based system you can do this. What you would do then is you work in chunks of items, and sort of each tuple sort of has a timestamp that will then determine when it has to move over to the next core, and this may of course potentially be a large amount of data you need to transfer. Right? This is inherent to the problem. But here, this simple example shows how you could do this in a simple nested loop join. So when a new tuple on R comes in, you have to compare with every element here in the S window. So assuming here tuple-based windows for the sake of simplicity. So you could either do that sequentially, or if you want to throw more silicon at it, you can instantiate multiple of these predicate evaluation circuits, and you can basically increase throughput here. If a tuple comes in on the S stream, you would basically do the same. Here in this case, you only have 4 comparisons. The window size not necessarily have to be the same size. The partition size on each stream doesn't need to be the same. So here is how we do that on the FPGA. On a single FPGA, the assumption is we have a unified core, so everything is synchronous. We have a clock network that's well distributed across the chip, so each core sort of works synchronously, and the data flows through the cores in lockstep mode. So essentially, we have a large shift register that shifts us the data in this direction, and a shift register in the opposite direction. Now, what we do, and here's the crucial point with joins potentially can produce a lot of data, depending on the hit rate of your join predicate. So depending on the estimation of your hit rate, you can go for high throughput here if you don't have many join result tuples. If you have many join result tuples, you may actually make sure that you siphon off the results fast enough from those cores. So at the end, you're data bound. And the way how we do this is through a merging network of FIFOs. And you can use different speeds for this reduction network and for the shifting network. So you have a couple of parameters we can play around with. So one is the speed we run this part of the circuit, and the other one is the speed of that circuit. And then we can play also with the fan-in we want to have on these FIFOs. If you zoom in on one of these cores, then it's really only a core as it appears on the chip. So we started our work first by the lack of traditional architectures that allow you this direct core-to-core communication, and we just now use the FPGA to simulate a new multi-core machine that has direct connections, that doesn't go through a shared memory, but that has direct connection to adjacent cores. And the data here moves in. They have data lines for each stream, input and output for the S stream. There's an output FIFO. There are two different clocks. One clock that operates the shifting circuit. The other clock up here operates the result, the join data circuits here, and that's this output FIFO. So this output FIFO is basically asynchronously operated by two clocks. There's still a problem. So at some point you may run into an overflow situation of that circuit. So what do you do then? Then your circuit is clearly in an overload situation. And what we do then is each core has this possibility to raise a throttle signal. Once this FIFO becomes about to be full, and then you are left with two options. So either you can start load shed, this traditional stream processing load shedding at the input. You're just discarding tuple, or otherwise you're just dropping results. Sandro?
If you look at the synchronous logic, it looks like a nice match, doesn't it?
Asynchronous logic, you mean?
Yes.
Yes. There's a nice story to that, how you can do this asynchronously. You have to be careful that if you're passing messages in this direction and in that direction, that you're not missing any match. But you can do this, and I didn't want to add this in the talk, but you can do this by sending acknowledgement messages in both directions. So it gives you then a relative order between the arrival on both streams. But this is exactly how this nicely also works in traditional multi-cores. Or across multiple FPGA chips. So, and I told you that we have this limited arm length, so we should have excellent scalability. So here's what happens. So we went and picked the largest Vertex 6 chip we could find. It's somewhat the 760T. That's why it took also 11 days to get the circuit running. And we varied the number of cores, of those computation cores, join cores on that chip. And as we increase the join core, we also increase the window size. So we are scaling, we are doing a weak scaling here. So there's a constant window size per node, so the window becomes larger linearly with the number of nodes. And here's the throughput we're getting in million tuples. So what you can see here, we are staying flat at roughly 20 million tuples, and then it slightly decreases. So the interesting point is you have linear scaling. So remember that the window size also increases with the number of cores. And the important point here is that there's no sudden drop to zero, because we have really only local interaction. Here at this point, we have to stop. We just run out of FIFO space. We're using BRAMs to implement the FIFOs. And we have here roughly used 96% of BRAM, so it's well beyond the recommended point of where you should sort of operate. But it nevertheless shows that this approach scales quite nicely.
Is this a simulation result, or did you actually?
So what we do is we put it on a real circuit. We run through the tool, so that's why it takes 11 days, and then we can sort of simulate it. So we basically back annotate the timing information in the simulation, and we can run to verify that it works. But even the fact that we are able to meet our preset timing constraints, and the tool was able to come up with a design that satisfies those constraints, tells us that ideally, if you would put this on a real physical chip, you wouldn't, hopefully, if the tools are correct, you would get the same results.
So
Yes?
the reduction in throughput is due to the reduction in the maximum clock rate?
Yes. So here, essentially, if you're using a simple eager nested loop join, you read 8 cycles to do the match per core. And this drop you can see here is because of reduction of in the clock rate, in the clock frequency. At this point here, what happens is you just know the optimizer has you just provide it no longer any room to operate, to navigate. So it's really reaching the saturation of the chip. So the other thing we were looking at is what are the optimal number of cores we can have. So assuming we now keep the window size constant and just vary the number of cores, right? Does it make sense to have many cores? Yes, because then the partition per core is slow, and we can have many. We sort of have many cores working in parallel on the same window, so we get throughput, high throughput. But the question is, if you instantiate many cores, we might actually get penalty in the clock frequency. So here's what happens. So this green line here shows the throughput, and the blue line shows the clock frequency. Clearly, the clock frequency has this kind of weird behavior. So if you have one core, means that we have a window of 1,000 elements processed by one core. We can operate at like 100 megahertz. If you go to 5 cores, we get to 150 megahertz. Then it suddenly drops, increases, and drops again. So this is an interesting observation here, in particular what happens over here. As we increase the core, the clock frequency here drops, such that we're not getting any more benefit for increasing the number of cores. So, yes?
Why does funny spike at low number of cores and jumps 50% and falls back
I have
again?
no idea. Probably one has to ask Xilinx why this is the case. Yes?
How sensitive was this to different place and route parameters? Like if you change the seed, would you get a different graph?
If you change the seed, it didn't change much, but it was extremely on the time constraints on both the FIFO, the FIFO merging network seems to play an extremely important role. So for these measurements, we were looking at the throughput. So the key metric was the shifting clock, and we sort of allowed the merging clock to become as low as possible. So that seemed to be, because in the end we're using most of the chip is occupied by the merging network. Yes?
So a question about the workloads. So are you doing an equi-join in this case? Is this an equi-join, equality join?
Yes.
Yes. Okay, and the data set itself is randomly generated, or is it, so are there kind of these spikes?
We don't need, that's the cool thing here in hardware. You're data independent, right? So.
But there could be this times during which the FIFO queues just get overrun, but then there will be times when we're looking at the ideal case where you're not output bound. So that's the setup. So the assumption is that the FIFO queues are not full. So wrapping up here at this point, the operator summary. This compiler, what can we support at this point? We have projection, selection, arithmetic and Boolean operation. We can do aggregation. I haven't shown you that. If the state of each aggregate is algebraic, which means it has a constant state, like sum, count, max, mean. If you want to do aggregation over holistic data, or holistic aggregates, for example, median, histograms, where you have potentially can have an unbounded amount of state, that doesn't really work that well on the FPGA. So the way around this is you would have to look into external DDR RAM, because you're just not able, you don't have enough state on the chip to maintain that. Windowing works. The grouping also is okay if you know upfront how many groups you're going to expect. And this works well in the stock exchange case, where the number of shares you're going to trade are sort of known advance. So the maximum number of groups you can handle is known a priori. And then you just instantiate as many parallel circuits, one for each group. The window join is the one I just presented. So before I really wrap up here, the last slide, and I want to avoid the questions coming here, so that's why I'm taking it right away. The question comes, what about GPUs? Why do I really have to go all the way down? And Here's the two simple key points here. GPUs cannot be put in the data path. Well, obviously. So you only have for GPU this type of setup here. And if you look at the work that was published on GPUs, they tend to keep these communication costs here sort of under the rock. You have to pay a lot of money basically to go from main memory to GPU memory and back. And in particular, database applications don't really work very nicely because you only need to touch the data maybe once or twice. So you don't have this high reuse of once you've copying the data. Of course, GPU is extremely fast when it comes to floating point operation and on tasks that can be tiled then sort of independent. It seems to be extremely difficult to use CUDA or OpenCL to implement this pipelining paradigm. And the last point here, I think that's one of the crucial, most important ones, is the power. So this is no longer or soon not any longer be one of the top-notch GPUs. They consume like 200 watts. And we could do something similar on the FPGA in the order of like tens or here in one particular case below 5 watts. So wrapping up, I think it's important here to rethink the algorithms. There's a brave new world of new hardware out there. What we've learned from the stream join is that if you start thinking out of the box, working on the FPGA, you're suddenly also able to basically backtrack that and translate it back into the CPU world. I'm happy to talk about offline how you can do stream join in traditional multi-cores. FPGAs can do stream processing too, in particular if you put them in the data path. And then I showed you Glacier, which is a compositional query to hardware compiler. Compositionally in terms that you can have nested plans, so it's a nested approach to this. And I showed you a kind of simple and hopefully could convince you that it's a simple and efficient implementation of the stream join. With that, I'm ending of the talk, and thanks for your attention. I'm happy to answer any questions. Thank you. Yes?
So do you optimize based on different queries that you can get that pipeline? You say you can collapse that pipeline into one stage. When you gave your example, like what heuristics are you guys using to try to decide how you collapse those? So
right now the optimization is quite crude. You're telling me what you want. Do you want throughput? Then I'm trying to keep in as many pipeline stages as possible. If you're telling me your latency or after, and we can tell what the latency is depending on the width of your data. So if you have very long comparison, like 64-bit comparisons, then we know that this is going to introduce a large delay on the signal path. So we are more likely to collapse if your comparison operations and predicates work on fewer data lines. So, but it's just over the thumb rule. It's kind of crude at this point. What you would like to have is a model that tells you what the resulting search is going to look like. I think there's work that's been done in the FPGA community that looks at cost models that tell you the benefits without actually having to go through the complete synthesis tool. Without actually going through the complete synthesis process. But right now it's quite very crude at the moment. Yes, please?
So when you do this handshake comparison with two streams kind of within one of the processing nodes or whatever you call it, being combined through, what is your strategy actually for the parallelism, for the comparisons that would happen there? I mean, you had on the slide, it said like predicate and some sketchy graphs, but because I mean that's also highly parallelizable depending on the throughput you're passing through.
Yes. That's indeed true. So right now the implementation we have, and I tell you that because it just went out of VLDB last week. What we have is a simple nested loop join. So that's definitely not. That's completely sequential. But of course, you're right. You can do much additional things. You may look at the compute. So, for example, if a new tuple comes in here, you may replicate that predicate logic and work on different elements on the window. Okay.
So this is, of course, straightforward for implementing a two-way join. I don't know anything about databases, but I would imagine that multi-way joining is something that's important. Could you kind of talk about how this would scale?
That's a good question. I sort of try to keep this under the rock. Okay, so here I have to talk about this. If you look at the semantics of the result tuples in a normal join, you have sort of temporal order, right? Now here, if you go through this merging pipeline, you have if multiple of these FIFOs have result data available, then you need to sort of arbitrate between these two. So at the very top, the order on which you see tuples is sort of still in order on what happens in the stream, but not quite. So in order to scale this up, you would have to basically add an operator that reorders the tuples, right? And then you can so that you have again a time sequence order of the tuples, so that the multi-way join as specified by the book would make sense in this case. But I don't think it's a real big problem because, first of all, in streaming systems, it's known that stream-based and the like, you don't really see that much stream-to-stream join happening in practice. Mostly it's stream-to-relation join. And in particular, n-way joins is something that's quite rare in practice.
Just implement the n-way join as a left deep sequence of joins as in traditional databases.
Yes, but if I have to make sure that I keep the semantics of the tuple order right? Otherwise, I get weird results. Well, I get results that wouldn't really make sense in the traditional way how n-way joins would be defined over Windows.
So this reordering operator, do you have a version of that in FPGA? To reorder it?
No, right now not, but it shouldn't be
it should not be a problem.
So the question is, of course, the n-way, this reordering operator would require state, right? So the complexity of that operator is then depending on the window size you have, right? So you should have twice the window size to keep the tuples to do the reordering.
Well, it's also a matter of buffering, because you have to be able to take all of the data from core N and hold it until you're positive that you've passed all the potential.
Well, you would basically place this core up here, right? And then you would get this stream, but you would have to reorder that stream.
Oh, okay.
But then you would have to introduce a timestamp anyway to have a clear semantics.
But even if you do have these timestamps, doing the reordering is not necessarily straightforward, because you don't know how you need to do it.
You of course you need yes. But what it boils down to, you have to pay just an upfront latency. I just need to you have some order information because of how the window size is, and if you wait long enough to know that you have seen all tuples that fall in this window where you have to do reordering. Then you can hold up all tuples up to then, and you just have to pay the latency for filling this buffer up. Sandro?
This can be implemented on multi-core. Did you do any comparisons between the two at any level?
What we did is on the multi-core we implemented time-based windows, and on the FPGA implemented tuple-based windows, and we compared the time-based implementation with the cell stream join. I don't know how we are in time, but I think I have the slide deck ready
for the people in SQL this afternoon. So maybe you can take this offline, if you, or I could.
Yeah, you got 30 minutes.
All right. Okay. All right. That's great. So I can. So here's what happens if you want to do asynchronous messaging between those previous cores. So what you do here between those cores is you add buffers, FIFOs essentially, and then you can have each core can operate with its own clock. And that cores then can be FPGAs, right? Or it can be multi-cores. So, and the problem I just sketched mentioning is what happens if a message is now tuple sent over here while one tuple is sent in the other direction, and they miss each other. So you don't have any join in that particular case. So what we now do is basically do in this two-way forwarding. And what we do is we assume now this core wants to send out R5, and this one wants to send out S4. He does that, sends it over into the FIFO queues in between, and then let's assume that this core here picks up this S4. And it does so. It does the following. It gets, while the transmission, while this tuple is in that queue, this core doesn't remove it yet. So basically says, well, I sent out this tuple, but I'm still responsible for matching it with anything that comes in. So what then happens here is assume that this guy now accepted S4, it joined it with S5, and then it will send here this diamond-shaped tuple and put it in this queue, and this is basically the acknowledgement, okay, I got it. And now the next thing is, let's assume this core here wants to send R6, so it can have multiple of these pending in that queue, and they would just pile up here. And at some point later, when this node here accepts S5, it would, again, because he hasn't received the confirmation for S4 yet, it will join it and send the acknowledgement back. Right. So what's happening here? And then, of course, it will receive, send the acknowledgement and get. So what happened here? Next step, this core sees the acknowledgement for S4, and then it can safely discard that tuple because it knows it is now taken care of by this other core. And so we shift one down. So what happens in here? You can avoid this missing join pair problem, but as you can see in this use case here, in this example, you will see duplicates, right? The R5 and S4 have been joined twice. So you need to see and the other problem is you need to have synchronization at the pipeline end, because if you put one in here, you have to sort of take one out on the other core, right? Because they're no longer moving in lockstep mode. And you can do this in sort of anti-tuples. So you put the tuple in here, you put in the anti-tuple on here, and it ends up in the same queue, and so you have then a relative ordering between. And this is sort of equivalent to Axe, and this has been done in other systems like the denial system with negative tuples or deletion messages. And so here's the data on a machine. So we run it on an Intel Nehalem AX. This is an 8 cores per die machine. We have four dies in one box. That machine is supposed to come out soon. But Intel was generous enough to give us one of these machines already.
And here's the data we're getting for different window sizes. As we increase the number of cores and the throughput, because the join is n squared in the order. If you increase n, you get a square root. So that's why I have this kind of square root curve, right? And this dashed line shows the estimated performance in the square root, and we're getting that for 5-minute windows, and we get it for 10-minute windows. The stream join paper, cell join paper by IBM, they're using the cell, which is 8 cores. They're a bit higher on 8 cores of what we can do here. It's just that the fact that the cell has this huge interconnect that it really allows you to stream. They're not really streaming. They don't have this pipeline type of processing, but they're doing spreading work between the main core and the SPs. But as you go up, so we also see excellent scalability on the multi-cores. That's this implementation is simple nested loop join. That's probably not what you want, because the LBM cell join paper they're using a SIMD optimized version, and have it heavily optimized. So what we can do now for the handshake join, that's what we call handshake on the pressure, is we're just doing merge join. So the first node at the stream will sort the data in a window, and then the data gets passed sorted, and we can only merge the sorted data, which basically reduces the cost of these merging elements, right? But of course, the sorting needs to be done at some point. And here's what happens. So that's the nested loop join, what we just saw. It's up down here. And we got a significant improvement in terms of speed if you're using merge join. However, see what happens up here. Here at this point, the data rate would be that high that we're getting tuples by the edge cores that are responsible for the sorting. That's why you're deviating from this ideal speed up. So this is kind of trying to put the things into contrast, what would happen on a traditional multi-core system. So I hope I haven't taken too much of your time. But,
This is some thousands.
This is 1,000 tuples. This is in the order of magnitude different than what we have on the FPGA. But these are time-based. These are time-based windows. And it's a lot. It's much more. Yes.
Okay.
But I mean, consider the state here. We have to ship that has to be shipped around, right? So there's you can imagine if you have a 10-minute, you have 4,000 tuples in a 10-minute interval. There's a lot of data. Yeah, and you can't. The comparison is not really fair. But we only wanted to show here that this approach, the scalability approach or idea works in both worlds.
So why again does the merge join kind of level off? Is it the overhead of sorting on one code that you're doing? Is it like
yes? For the merge join, the data is processed in chunks. So the way we use, that's motivated by the work of the people doing in Barrelfish around Timothy Roscoe. So we basically piggybacking. We're doing the node core-to-core communication by piggybacking the cache coherency protocol. So we basically implement this FIFO queue as in units. In message units of 128 element blocks. That's what the amount we ship atomically in between. And at some point, the sorting that needs to be done by the first node in order to do the merge join, which reduces the work for everybody else, that sorting starts to dominate for this. As the more cores you add, the higher you can possibly increase the throughput. So these numbers are, of course, obtained differently than for the FPGA. So what we just run, we're tuning on the speed of our data generator until we fell over, right?
until suddenly the system started to sort of.
So you could also potentially do the multi-phase sorting, right? Sort in phases and then merge them so that you can scale it up to multiple cores. So
Yeah, you might think of.
so you don't have to.
Yeah, but still, the fact that at one core sort of needs to do some coordination work, and the coordination work is the sorting, prevents you from going along this ideal speed up.
Fundamentally, it's because the algorithm, the order of the algorithms are just different. Well, I guess let's thank our speaker again.
Thank you for your time.